There is a place, not far by cosmic standards, where our sun has dimmed to little more than a bright star among stars, where its warmth no longer reaches, where the solar wind, that constant invisible breath that our star exhales in all directions, finally runs out of strength and gives way to the cold interstellar medium beyond. This place is not in a distant galaxy. It is not in another star system. It is in our own backyard, the outermost reaches of our own solar family, a region so dark, so cold, and so vast that we have only recently begun to develop the instruments capable of probing it. Out there, in that frozen darkness beyond the last known planets, beyond the scattered debris of icy bodies that trail outward for perhaps a light year in every direction, something may be waiting. For decades, astronomers have suspected the presence of a large undiscovered world in the far outer solar system. They have called it, carefully and provisionally, Planet 9, not because they have seen it, but because the solar system itself seems to lean in its direction. The orbits of distant bodies appear to be nudged, pulled, influenced by something massive and unseen, like iron filings orienting toward an invisible magnet. Tonight, we journey to the outermost reaches of our solar home. We will trace the patient, century-long search for a ninth planet. We will explore the evidence, careful, accumulating, scientifically honest, that something large may move in the darkness beyond Neptune. And we will sit quietly with the remarkable possibility that, within our own solar system, a world the size of several Earths may have remained hidden until now. There is nothing hurried about this journey. The outer solar system does not move quickly, nor shall we. If you love exploring the cosmos, a like and subscribe would mean the world to us. Let's begin. Most of us carry in our minds a picture of the solar system, 8 planets arranged in order from the Sun, their orbits drawn as clean ellipses on a flat plane. Mercury closest, then Venus, Earth, Mars, the rocky inner worlds, then the asteroid belt, then Jupiter, Saturn, Uranus, Neptune, the gas and ice giants, massive and distant. And beyond Neptune, a kind of edge, the end of the familiar. This picture is true as far as it goes, but it is profoundly incomplete. The solar system does not end at Neptune. It extends in ways that are still being mapped and understood for distances that dwarf everything within it. Beyond Neptune begins a region called the Kuiper Belt, a wide disc-shaped zone extending from roughly 30 to 50 times the Earth-Sun distance, populated by icy bodies, dwarf planets, and the remnant debris of the solar system's formation. Pluto, reclassified as a dwarf planet in 2006, resides within the Kuiper Belt, along with hundreds of other known objects and perhaps thousands more awaiting discovery. Beyond the Kuiper Belt, the solar system continues still. A region called the scattered disk extends further outward, where gravitational interactions with Neptune have flung icy bodies into elongated, unstable orbits. And beyond even that, theorists believe, lies the Oort cloud, a vast spherical shell of icy objects extending perhaps 1 to 2 light-years from the Sun in every direction, the source of long-period comets that occasionally visit the inner solar system on journeys that take thousands of years. The solar system is not a tidy arrangement of 8 planets. It is an enormous, complex, still largely unexplored system, whose outermost reaches extend nearly a quarter of the way to the nearest star. And it is in those reaches, in that cold, dark expanse beyond the Kuiper Belt, that our story tonight truly begins. The idea that a large, unseen planet might lurk in the outer solar system is not new. It has a long and genuinely fascinating history, one that tells us as much about the methods of science as it does about the solar system itself. In the 19th century, astronomers noticed something troubling about the orbit of Uranus. Discovered by William Herschel in 1781, Uranus moved through its orbit with a slight but measurable deviation from the path that Newtonian gravity predicted. Something was pulling it, something unseen. 2 mathematicians, John Couch Adams in England and Urbain Le Verrier in France, independently calculated where an undiscovered planet would need to be in order to produce those deviations. In 1846, the German astronomer Johann Galle pointed his telescope at the position Le Verrier had predicted and found Neptune. exactly where the mathematics said it would be. It was one of the most striking intellectual triumphs in the history of science. A planet discovered not by observation, but by calculation. Found because it left a gravitational fingerprint on the behaviour of its neighbour. In the early 20th century, the search for another unseen world, which astronomers then called Planet X, continued. Perceived deviations in the orbits of both Uranus and Neptune suggested, to some observers, a further perturbing body. This search led Clyde Tombaugh to discover Pluto in 1930. Though Pluto, it eventually became clear, was far too small to produce the orbital anomalies that had motivated the search. Those anomalies were later found to be measurement errors, and the gravitational case for a Planet X of the original kind dissolved. But something of the idea persisted. The outer solar system, vast and poorly mapped, seemed to many astronomers too large and too dark to have been fully inventoried. The modern search for Planet 9 picks up this thread, with better data, better methods, and a more compelling body of evidence than any previous chapter in the story. To understand why astronomers believe Planet 9 may exist, we need to understand the objects that have given them pause, the distant bodies of the outer solar system whose behaviour does not quite fit our models. Beginning in 2003 and continuing through subsequent years of survey work, astronomers began discovering objects in the outer solar system with orbital properties that seemed, at first, merely unusual. These objects, some of them quite small, some potentially dwarf planet-sized, had extremely elongated orbits. They plunged far into the outer solar system at their most distant points, then swung back relatively close to the Sun at their nearest approach. This was not, in itself, surprising. What was surprising was the direction in which these orbits pointed. Imagine a series of elongated ellipses arranged around the Sun. If there were no large external perturbing body, you would expect those ellipses to point in random directions, scattered around the compass, so to speak, like spokes of a wheel pointing every which way. This is what gravitational scattering by Neptune and the orbital dynamics of the outer solar system should produce over billions of years. But the most distant of these objects, the ones with the most elongated orbits, the ones that travel furthest from the Sun, showed a strange clustering. Their orbits pointed preferentially in the same general direction, and their orbital planes tilted in ways that, collectively, seemed to echo a common influence. In 2016, astronomers Konstantin Batygin and Michael Brown published a careful analysis of 6 of these distant trans-Neptunian objects. Their finding was measured but striking. The probability of this clustering occurring by chance was approximately 1 in 14,000. Something appeared to be organising them, something massive, distant, and as yet unseen. They proposed a planet, roughly 10 times the mass of Earth, orbiting the Sun at an enormous distance, that could, through its gravitational influence over billions of years, produce precisely the clustering they observed. Planet 9 had a hypothesis. Now it needed a search. Let us imagine for a moment what Planet 9 might be, if it exists. Based on the orbital mechanics of the distant objects it appears to influence, astronomers have estimated its likely properties with reasonable confidence. It would be a world roughly 2 to 10 times the mass of Earth, making it what planetary scientists call a super-Earth, or possibly a mini-Neptune. Significantly larger than our own planet. Significantly smaller than Neptune, which is about 17 Earth masses. Its orbit around the Sun would be extraordinarily elongated. At its closest approach, called perihelion, it might be as near as 300 times the Earth-Sun distance. At its farthest point, aphelion, it might venture to perhaps 900 or 1,000 times the Earth-Sun distance. Its orbital period, the time it takes to complete one full circuit of the Sun, would be somewhere between 10,000 and 20,000 years. Let that settle for a moment. While one complete year passes on Earth, while the seasons turn through their full cycle, Planet 9, in its orbit, would move so slowly that it would cover only a tiny fraction of a degree against the background stars. Finding it requires knowing not just where to look, but when, and having instruments sensitive enough to detect the faint cold light it reflects from a sun so distant that it appears as little more than a bright star. At such a distance, Planet 9 would be extraordinarily cold. Its surface temperature, if it has a solid surface, would be close to absolute zero. Any light it reflects from the Sun would be faint beyond casual detection. The only telescope systems capable of finding it must gather light with extreme sensitivity across long observation times. It would be a world of permanent total darkness, if darkness is even the right word for a place where the Sun is too dim to illuminate. A world of frozen gases, ancient and still, drifting in silence through the outermost reaches of our own solar family. If Planet 9 exists, and this remains, as of the time of writing, a hypothesis rather than a confirmed discovery, how did it come to be so far from the Sun? How does a planet end up in such an extreme orbit, so distant from the warmth and activity of the inner solar system? Planetary scientists have proposed several formation pathways, each grounded in our understanding of how solar systems assemble and evolve. The most widely discussed possibility is ejection from the inner solar system. In the earliest epochs of our solar system, the first hundreds of millions of years, when the giant planets were migrating to their current positions, gravitational interactions were chaotic and intense. The giant planets, particularly Jupiter and Saturn, were powerful sculptors of the solar system's architecture. Objects that came too close to these giants were flung outward, some onto hyperbolic trajectories that ejected them entirely, others onto highly elongated orbits that kept them loosely bound to the Sun at enormous distances. If a planetary embryo, a protoplanet that had accumulated significant mass in the region of Uranus and Neptune, received a gravitational kick from Jupiter or Saturn at the right angle and the right time, it could have been sent into exactly the kind of distant, elongated orbit that Planet 9 is hypothesized to occupy. It would not have been lost entirely, just misplaced. Sent to the outermost edge of the family it was born in, where it has been circling slowly and silently for 4.5 billion years. An alternative hypothesis suggests that Planet 9 may have formed in place, in the cold outer reaches of the solar system's protoplanetary disk, where material was sufficient over time to build a substantial world. This pathway is less favoured, as the disk at such distances is thought to have been too sparse and slow-moving for efficient planetary accretion. A third, more speculative idea proposes that Planet 9 may have been captured, that it originated in another star system and was gravitationally acquired by our Sun during the early period, when stars were densely clustered in a stellar nursery. Stars in their youth are relatively close together, and planetary exchanges, though rare, are not theoretically impossible. Which pathway is correct, if any, depends on confirmation of the planet's existence and careful measurement of its orbit. The story of its origin remains open. Finding an object at the hypothetical distance of Planet 9 is an exercise in extraordinary patience and precision. Consider the challenge. At 3 to 10 times the distance of Neptune, itself nearly 4.5 billion kilometers from the Sun, Planet 9, if it exists, reflects only a tiny fraction of the already diminished sunlight that reaches it. The further an object is from the Sun, the less light it receives, and the less it reflects back toward Earth. The relationship is steep. Double the distance, and the reflected light drops by a factor of 16. At Planet 9's hypothetical distances, even a world the size of several Earths would appear extraordinarily faint. Ground-based telescopes have surveyed large swaths of sky looking for slow-moving objects that might match Planet 9's predicted properties. The challenge is not merely sensitivity but coverage. Planet 9 could be anywhere along a broad arc of sky, its orbital path not yet pinned down precisely enough to narrow the search to a small region. Several wide-field survey telescopes have been brought to bear on the problem. The Dark Energy Survey, a wide-field imaging project that mapped several thousand square degrees of sky in the southern hemisphere, was searched for Planet 9 candidates. The Subaru telescope in Hawaii, with its hyper-suprime cam, one of the widest field optical cameras ever built, has conducted dedicated surveys. And then there is the Vera C. Rubin Observatory, now entering operation in Chile, whose legacy survey of space and time will image the entire visible southern sky every few nights with extraordinary depth. When fully operational, it is expected to either discover Planet 9 or constrain its properties to the point where its existence or non-existence can be assessed with much greater confidence. And orbiting above all of this, above Earth's distorting atmosphere, cooled to temperatures close to absolute zero, sensitive to infrared wavelengths that ground-based telescopes struggle to reach. The James Webb Space Telescope provides a uniquely powerful tool for this search. The James Webb Space Telescope was not designed primarily as a planet-hunting instrument for our own solar system. Its primary scientific missions centre on the early universe, the first stars and galaxies, the atmospheres of exoplanets, the chemistry of star-forming regions. Its golden mirror and suite of infrared instruments were optimized for peering across billions of light-years into the cosmos. And yet, by virtue of its extraordinary sensitivity to infrared light, its position above Earth's atmosphere and its stable, cold operating environment, Webb possesses qualities that make it remarkably well suited to search for a cold, dark, distant world in the outer solar system. Here is the essential physics. An object as cold as Planet 9 would be, at temperatures close to absolute zero, radiates almost no visible light, but it does emit, very faintly, in the thermal infrared. It also reflects what little sunlight reaches it. At the wavelengths where Webb operates, a cold distant world may be detectable in ways that visible light telescopes cannot achieve. Moreover, Webb's angular resolution, its ability to distinguish fine details and detect faint point sources against the background sky, is among the finest of any operating telescope. When pointed at a region of sky where Planet 9 might reside, and when multiple observations are taken across an interval of days or weeks, Webb can detect the slow movement of a nearby solar system object against the fixed background of distant stars. This movement, called proper motion, is the signature that distinguishes a solar system body from a background star or galaxy. The key is patience and the accumulation of observations at the right times, in the right part of the sky. In recent observing programs, building on the orbital predictions refined by years of trans-Neptunian object surveys, Webb has been directed towards selected regions of sky that models suggest are most likely to contain Planet 9. The results of these observations, as they come in and are analysed, represent the sharpest edge of an ongoing and genuinely exciting investigation. The case for Planet 9 rests on an accumulating body of evidence from the orbits of distant trans-Neptunian objects, bodies orbiting the Sun beyond Neptune at extreme distances. Since the initial 2016 analysis by Bettigen and Brown, the number of known extreme trans-Neptunian objects has grown. Additional surveys, including the Outer Solar System Origin Survey and the Dark Energy Survey, have catalogued more objects, and the analysis has been revisited multiple times with updated data. The picture that emerges is this: objects with semi-major axes, the average of their closest and farthest orbital distances, beyond approximately 250 times the Earth-Sun distance, show a statistically significant tendency to cluster in their orbital orientation. Their orbital poles, the axes perpendicular to their orbital planes, point in preferred directions. Their perihelion directions, the points in their orbits where they are closest to the Sun, show grouping that would be unexpected in the absence of a perturbing body. Some researchers have critiqued this analysis, arguing that observational bias, the fact that our surveys preferentially observe certain regions of sky, could artificially produce the appearance of clustering. If most of the telescope time that discovered these objects was spent looking at certain parts of the sky, then the objects found would naturally cluster there, regardless of any real physical cause. This debate is honest and scientifically healthy. Bettigen, Brown, and their collaborators have worked to account for these biases, and their most recent analyses continue to find a residual signal that they argue cannot be fully explained by observational selection effects alone. Independent teams have also examined the problem and found supporting evidence. The orbital inclinations of some distant objects, the degree to which their orbital planes are tilted relative to the main plane of the solar system, also show patterns consistent with the influence of a distant inclined planet. The evidence is not conclusive, but it is serious, carefully examined and growing with each new survey. One of the most important developments in the Planet 9 search has been the progressive refinement of its predicted location. In the years since 2016, as more distant trans-Neptunian objects have been discovered, and as the orbital analysis has been refined, the predicted sky position of Planet 9 has been narrowed. Rather than a search spread uniformly across the entire sky, an enormous and arguably intractable task, The hypothesis now points to a preferred region. Planet 9, if it exists, is currently predicted to be somewhere in a broad arc of sky in the southern celestial hemisphere, potentially near the constellations Gemini or Orion, though the precise location depends on which orbital model one uses and which set of trans-Neptunian objects one includes in the analysis. Different teams have published somewhat different predictions, reflecting genuine uncertainty in the underlying data. The predicted distance, somewhere between 300 and 700 astronomical units from the Sun, with the most likely estimates clustering around 500 astronomical units, places it within the range of Webb sensitivity for a sufficiently massive and cold object. What does a targeted Webb observation look like? In practice, astronomers would select a promising region of sky and observe it at 2 or more epochs, separated by days or weeks, with Webb's near-infrared camera or mid-infrared instrument. A solar system object at the predicted distance would show measurable movement between those epochs. The movement would be slow, a fraction of an arc-second per hour, but detectable by Webb's precise pointing and stable imaging. If an object is found that moves at the right rate, in the right direction, with the right infrared brightness consistent with a cold, large, distant world, that would be a candidate detection. Confirmation would then require follow-up observations to map the orbit and verify that it is consistent with the Planet 9 hypothesis. This is the process. Patient, methodical, and building towards something that could, when confirmed, rank among the most significant discoveries in the history of planetary science. As we wait on the question of Planet 9 itself, let us spend some time with the objects that made its existence seem plausible. The extreme trans-Neptunian objects, abbreviated ETNOs, are in their own right extraordinary members of our solar family. Among the most distant and unusual of these is an object called Sedna, discovered in 2003 by Mike Brown, Chad Trujillo, and David Rabinowitz. Sedna orbits the Sun at a distance that ranges from approximately 76 to over 1,000 times the Earth-Sun distance. Its orbital period is estimated at approximately 11,000 years. At its farthest point from the Sun, Sedna is among the most isolated objects in the solar system, too far from Neptune to have been scattered there by gravitational interaction with that planet, and in an orbit that our standard models of solar system formation struggle to explain. It was Sedna, in many ways, that first suggested that something unusual was shaping the architecture of the outer solar system. More recently, an object called 2012 VP113, nicknamed Biden by its discoverers, a gentle reference to the vice presidential initials, was found in an orbit similar in some respects to Sedna's, and subsequent surveys have added more ETNOs to the catalogue, each one adding a data point to the pattern that points toward Planet 9. These objects are small, likely irregular, icy, and dark. They reflect very little of the already faint sunlight that reaches them at such distances. Their surfaces are ancient, undisturbed by the geological activity that reshapes the inner solar system's worlds, and likely coated with irradiated organic material, dark as coal, that has been modified over billions of years by cosmic rays and ultraviolet radiation. They are silent travellers, patient, enduring. And in their orbits, they carry the gravitational memory of whatever shaped them, a record that careful analysis is beginning, slowly and painstakingly, to decode. Before we move further outward into the hypothetical, let us rest for a moment with the most famous of the outer solar system's inhabitants. Pluto, discovered in 1930, reclassified in 2006, and visited in intimate detail for the first time in 2015 by the New Horizons spacecraft. Pluto was, for 76 years, considered the 9th planet. Its reclassification as a dwarf planet, a decision by the International Astronomical Union based on the definition of planethood, was scientifically well-grounded but culturally resonant. Many people feel a genuine affection for Pluto that few other scientific objects inspire. What New Horizons revealed when it flew past Pluto at a distance of about 12,000 kilometers was startling in its richness. Pluto is not a dead, featureless ice ball. It has mountains of water ice rising 3,000 meters above its surface. It has vast plains of nitrogen ice Tombor Regio, named for Pluto's discoverer, that appear geologically young, their surfaces renewed by slow convective movement of the ice itself. It has a thin but complex atmosphere. It has a heart, a literal heart-shaped region of bright terrain that has become the most recognizable feature of this distant world. Pluto has a large moon Charon, which is so massive relative to Pluto that the two bodies orbit their common center of gravity, a point that lies in the space between them outside Pluto itself. They are in a sense a double world, and Pluto is not alone in its orbital neighborhood. A family of objects called Plutonos share Pluto's orbital resonance with Neptune, completing 2 orbits for every 3 that Neptune completes. Hundreds of Kuiper Belt objects are known. Thousands more likely exist awaiting discovery. The outer solar system is not empty. It is full. It is ancient. And it stretches through the Kuiper Belt and the scattered disk and the hypothetical realm of Planet 9, and beyond that to the Oort cloud, for distances that make even Neptune seem close. Beyond the Kuiper Belt, beyond the scattered disk, beyond even the hypothetical realm of Planet 9. There is a place we have never directly observed, a place inferred entirely from the behaviour of the objects that occasionally visit the inner solar system. It is called the Oort cloud. Named for the Dutch astronomer Jan Hendrik Oort, who proposed its existence in 1950, the Oort cloud is thought to be a vast spherical shell of icy bodies surrounding the solar system at distances of roughly 2,000 to 100,000 astronomical units from the Sun. At its outer edge, it may extend nearly 2 light years, almost halfway to the nearest star. The Oort cloud is believed to be the source of long-period comets, those comets that arrive in the inner solar system on orbits that take thousands or even millions of years to complete, appearing as if from nowhere and receding again into the deep. Their highly elongated, steeply inclined orbit suggests they were nudged inward from an enormous reservoir at the solar system's periphery. That reservoir is the Oort cloud. The total mass of the Oort cloud is uncertain, but is thought to be several times the mass of Earth, distributed among an estimated 1 trillion or more icy objects. Yet no individual Oort cloud object has ever been directly observed. At such distances, even the largest objects would be far too faint for current instruments. What occasionally dislodges a comet from the Oort cloud and sends it sunward? Several mechanisms have been proposed. The gravitational influence of passing stars, which over millions of years occasionally come close enough to perturb Oort cloud objects. The passage of the solar system through dense regions of the galactic disk. Possibly the gravitational influence of Planet 9 itself, whose highly elongated orbit might, at its farthest points, reach into the inner Oort cloud. The Oort cloud is the solar system's outermost veil, immense, diffuse, and entirely invisible to us. Its existence is one of the most confidently held inferences in planetary science, and one of the most humbling reminders of how much of our own solar neighbourhood remains beyond direct human observation. There is something deeply meditative about the act of searching for a world you cannot yet see. It requires a particular quality of attention, sustained, patient, open to ambiguity, and comfortable with the possibility that the answer may take years to arrive. Astronomers hunting for Planet 9 work with a toolkit that combines observational survey work with theoretical modelling, computational simulation, and statistical analysis. Each discipline informs the others. The surveyors find objects. The theorists model their orbits. The statisticians assess whether the patterns are real or illusory. The computational scientists simulate what the solar system would look like over billions of years, with and without a distant massive planet, and compare the predictions to observation. Observationally, the search relies on a technique called blink comparisons, a method that is, in concept, ancient but in execution, increasingly sophisticated. By comparing images of the same region of sky taken at different times, any object that has moved between exposures will appear to jump back and forth, blinking, against the fixed stars. This is how Clyde Tombaugh found Pluto in 1930, by blinking photographic plates. Modern versions of this technique use automated computer algorithms to search thousands of image pairs simultaneously, flagging moving objects for human review. The challenge with Planet 9 is that it moves very slowly, more slowly than any previously discovered planet, because it is so far from the Sun. Detecting its motion requires either very widely separated observation epochs or extremely precise positional measurements. This is where Webb offers particular advantages. Its stable platform, free from the blurring effects of Earth's atmosphere, and its precise pointing allow it to make positional measurements of extraordinary accuracy. If an object in the predicted region of sky shows the specific movement signature of a distant solar system body, Webb will, in principle, be able to detect it. The search is methodical, it is careful, and it is genuinely among the most exciting open questions in planetary science. As we consider the case for Planet 9, intellectual honesty requires that we also consider the alternatives. Science, at its best, holds all hypotheses simultaneously until the evidence speaks clearly enough to favour one. Several researchers have proposed that the clustering of extreme trans-Neptunian objects may not require a distant massive planet at all. One alternative explanation invokes observational bias more strongly, suggesting that the tendency to survey certain regions of sky, combined with the relatively small sample of known extreme TNOs, could produce apparent clustering through selection effects rather than real physical grouping. This argument has been made carefully and in peer-reviewed literature, and it deserves serious attention. Another hypothesis proposes that the outer solar system's structure could be explained by a diffuse disk of smaller bodies, a remnant population from the early solar system, rather than a single large planet. This disk, if it existed and had sufficient total mass, could exert gravitational influences on extreme TNOs that mimic some of the effects attributed to Planet 9. A third possibility, sometimes called the primordial black hole hypothesis, was proposed in 2019 by Jakub Scholz and James Unwin. They suggested speculatively that what we are interpreting as the gravitational influence of an unseen planet might instead be a very small black hole, a remnant of the early universe, orbiting our Sun at the appropriate distance. A black hole of roughly 5 Earth masses at such a distance would be gravitationally indistinguishable from a planet of similar mass. It would be extraordinarily difficult to detect, as it would emit no reflected light and only the faintest Hawking radiation. This hypothesis is fascinating but currently untestable with available instruments. What distinguishes these alternatives from the Planet 9 hypothesis is their testability. A distant planet will eventually be found, or definitively not found, by surveys like the Rubin Observatory's Legacy Survey. A planet that should exist and does not appear, across a complete unbiased survey of the entire sky to the necessary depth, would strongly disfavour the hypothesis. The truth, patiently sought, will emerge from the data. One of the quieter revelations of the Planet 9 investigation is the way it has deepened our appreciation for the solar system as a dynamic, evolving system, not a static arrangement that has always looked as it does today. For most of human history, the solar system was conceived as orderly, clockwork-like, and essentially permanent. The planets moved in their orbits, predictable and stable. The sun shone. The arrangement seemed fixed. We now understand that the solar system has had a turbulent past. In its first 100 million years, a period called the Late Heavy Bombardment, or the Grand Tack, the giant planets may have migrated significantly from their formation positions. Jupiter, current models suggest, may have moved inward toward the Sun and then back outward again, scattering objects throughout the solar system in the process. Saturn, Uranus, and Neptune also migrated. Neptune, in particular, is thought to have moved significantly outward from its formation location, sculpting the Kuiper Belt in the process. This dynamism had consequences throughout the solar system. The asteroid belt, which might have been far more populated, was depleted by Jupiter's gravitational clearing. The inner planets, including Earth, were bombarded with material flung inward by the giant planet's migration. The water on Earth's surface may owe its presence in significant part to water-bearing objects that were scattered from the outer solar system during this chaotic early period. The outer solar system's architecture today, the Kuiper Belt, the scattered disk, the extreme trans-Neptunian objects, the hypothesized Planet 9, is the archaeological record of this early dynamism. Reading it requires understanding the processes that shaped it, and understanding those processes requires that we know all the significant actors. If Planet 9 was flung to its current distant orbit during the early dynamism of the solar system, then accounting for it is essential to constructing an accurate history of our entire solar neighbourhood. It is a story of origins, and every solar system body is a chapter. There is something worth pausing to appreciate about the particular kind of patience that planetary science requires. Astronomers searching for Planet 9 may work for years, perhaps an entire career, toward a discovery that may or may not come in their lifetimes. The survey work is meticulous and repetitive. The data analysis is careful and subject to ongoing debate. The predictions shift as new objects are discovered and old analyses are revised. Progress is real but rarely dramatic. This is not unusual in science. The history of astronomy is populated by searches that took generations. The hunt for Pluto stretched across nearly 3 decades before Tombaw's discovery in 1930. The theoretical framework for understanding stellar evolution, how stars are born, how they live, how they die, was built over the course of a century by hundreds of astronomers whose individual contributions seemed modest, but whose collective work transformed our understanding. The Planet 9 search inherits this tradition. Battergin and Brown, who have been central to the modern hypothesis, have spoken in various interviews about the mixed feelings of searching for something you believe is real but cannot yet confirm. There is an intellectual excitement in the evidence. There is also uncertainty. The possibility that the clustering is a statistical artifact, that observation bias has played tricks on the data, remains live and is taken seriously. What sustains the search aside from the intellectual beauty of the problem is the improving quality of the tools. Each generation of survey telescopes sees further covers more sky and produces data of higher quality than the generation before. The Rubin Observatory will image the entire visible sky repeatedly over a decade, building a data set of unprecedented completeness. Webb provides complementary depth in targeted regions. Between them, they represent a capability for outer solar system discovery that simply did not exist a generation ago. The question that has captivated planetary scientists for a decade is approaching slowly a definitive answer. Let us imagine quietly what the confirmed discovery of Planet 9 would mean. It would first complete, or rather extend, the census of our solar system. For the first time since the discovery and subsequent reclassification of Pluto, the solar system would have gained a new world, a true planet by the criteria that define planethood, massive enough to dominate its orbital neighbourhood, large enough to be rounded by its own gravity, orbiting the Sun as a primary body. It would answer at least partially the long-standing question of what has been organising the orbits of extreme trans-Neptunian objects. It would validate a methodology, the use of orbital perturbations, to infer unseen bodies that stretches back to the discovery of Neptune in 1846. It would open an entirely new field of study. A world of several Earth masses in the far outer solar system would have its own geological history, its own thermal evolution, its own perhaps retained heat from formation. Understanding it would require dedicated mission spacecraft that, given the distances involved, would take decades to reach. The planning for such missions would begin immediately with the knowledge that the scientists who initiate those plans might not live to see their conclusions. For the rest of us, for those who look up at the night sky and feel that nameless feeling of connection to something vast and ongoing, the discovery would offer something simpler and more immediate. It would remind us that our own solar system, the neighbourhood where our world lives, is still yielding surprises, that the map is not yet complete. That discovery, even close to home, continues. The universe does not withhold its wonders all at once. It reveals them gradually to those patient enough to look. There is a particular kind of thought that scientists sometimes allow themselves, a thought about the future, about who will be the ones to finally confirm what the data only suggests today. The students studying astrophysics right now, the ones poring over papers on trans-Neptunian object orbits, learning to process survey data, building the computational tools that will search the Rubin Observatory's imaging datasets. These are the people most likely to make the final determination about Planet 9's existence. They are in university lecture halls and research groups around the world. Many of them have not yet had the conversation or conducted the analysis that will be decisive. This is in its way a beautiful thought. Science is not merely an institution or a methodology. It is a living inheritance, a body of questions and techniques, and knowledge passed from generation to generation, each cohort extending the reach of the last. The astronomers who first mapped the outer solar system in the late 19th century could not have imagined the instruments their successors would build. The scientists of the 20th century who theorized about trans-Neptunian populations could not have known that Webb would someday probe their predictions. The generation now entering science inherits a set of tools, Webb Rubin, the accumulated catalogue of trans-Neptunian objects, the refined orbital predictions that make a definitive answer to the Planet 9 question achievable within a decade, possibly less. And whoever makes that discovery, whoever processes the data or writes the code or notices the faint, slow-moving point of light against the background stars will join a tradition that stretches from Herschel, discovering Uranus in 1781, to Galle finding Neptune in 1846, to Tombaugh locating Pluto in 1930. A tradition of patient, careful, persistent attention to the darkness at the edge of things. They will look where others have looked and have not found, and they will find. We have spoken about distances in astronomical units, shorthand for the average distance from Earth to the Sun, roughly 150 million kilometres, and we have noted that Planet 9 is predicted to orbit at perhaps 500 astronomical units. But numbers alone do not convey the true scale of what we're discussing. Let us try a different approach. Imagine the solar system shrunk so that the Sun is the size of a grapefruit, roughly 10 centimetres across. At this scale, Earth orbits approximately 10 metres from the Sun. Neptune, the outermost confirmed planet, would be at roughly 300 metres, about 3 football fields from the grapefruit Sun. Planet 9, at 500 astronomical units, would be at approximately 5 kilometres from the grapefruit. 5 kilometres. The Oort cloud's outer edge, at 100,000 astronomical units, would be at approximately 1,000 kilometres. Roughly the distance from New York to Chicago, or from London to Gibraltar. All of this around a grapefruit. And the nearest star, Proxima Centauri, the closest stellar neighbour to our Sun, would be, at this scale, approximately 27,000 kilometres away. Just over 2/3 of the way to the Moon. These comparisons do not make the solar system feel smaller. They make it feel larger, more correctly large than our minds naturally hold it. The outer solar system, the domain of Planet 9 and the Oort cloud, is not a modest extension beyond the familiar planets. It is an enormous expanse that makes the familiar inner solar system, where Earth and Mars and Jupiter reside, seem like a tiny cluster of objects near a central light. And all of this, everything within our Sun's gravitational reach, from Mercury to the outermost Oort cloud object, is contained within a bubble of space less than 2 light-years across. Our Milky Way galaxy is 100,000 light-years across. There are 100 billion stars in our galaxy. We are, as always, small, and the system we live in, which we have only begun to fully map, is itself only the tiniest of neighbourhoods in something incomprehensibly larger. As we approach the end of our journey tonight, let us gently zoom out further still. From the outer solar system, from the hypothetical realm of Planet 9 and the ancient expanse of the Oort cloud, to the galaxy that contains us. Our Sun is one star among an estimated 200 to 400 billion in the Milky Way. It orbits the galactic centre at a distance of approximately 26,000 light-years, completing one full circuit in roughly 230 million years. The last time our Sun was in its current position in the galaxy, the age of dinosaurs was just beginning on Earth. Our solar system moves through the Milky Way at approximately 220 kilometers per second relative to the galactic centre. We pass through different regions of the galaxy over time, occasionally through denser molecular clouds, occasionally closer to regions of active star formation, with their accompanying radiation and stellar activity. This motion has consequences for the outer solar system. The passage of nearby stars, relatively rare but not impossible over geological time, can perturb the Oort cloud, sending comets inward. The varying gravitational field of the galactic disk exerts tidal forces on the outermost reaches of our solar system. Even the galaxy's spiral arms, which we pass through on our galactic orbit, may influence the architecture of the outer solar system over hundreds of millions of years. In this sense, our solar system is not an isolated, self-contained system. It is embedded in a galaxy. It interacts with its galactic environment. The outer solar system, the realm we have been exploring tonight, is the interface between our Sun's immediate gravitational domain and the larger galactic environment in which it moves. Planet 9, if it exists, occupies precisely this frontier zone. It would be, in a sense, a bridge between the purely solar and the galactic, influenced by both, belonging fully to neither. It is a frontier in the most literal meaning of the word. Perhaps one of the quietest and most overlooked aspects of the Planet 9 story is what it says about our relationship with home. We tend to think of exploration as something that happens far away. We look outward, to exoplanets around distant stars, to galaxies at the edge of the observable universe, with a sense that the frontier lies in the distance, that what is close has already been known and catalogued and put away. The possibility of Planet 9 gently corrects this assumption. Our own solar system, the system we inhabit, the gravitational community our world belongs to, is still being inventoried. We have not finished meeting the family. There may be a world, right here in our own solar neighbourhood, that we have not yet introduced ourselves to. A world that has been orbiting the same star as Earth for 4.5 billion years, tracing its slow ellipse in the outer dark, entirely unknown to the creatures who evolved on its innermost neighbour. This is not a failure. It is a reminder of how large home is. The solar system's outer reaches are not easily surveyed. They require instruments of extraordinary sensitivity and the patience to use them carefully over long timescales. The fact that we are now, for the first time in history, genuinely capable of conducting that survey, with Webb, with Rubin, with the accumulated methods of a century of planetary science, is itself remarkable. We are completing the map, slowly, carefully, square by square. And in the parts that remain blank, something significant may still be waiting. The inventory of home is not finished. That is a wonderful thing. The outer solar system exists in a silence that is different from ordinary silence. It is not the silence of emptiness, though it is certainly sparse. It is the silence of immense distance, of cold and dark so thorough that the sun, the warm source of all light and energy for the inner planets, has dwindled to a point among points, a bright star, nothing more. In that silence, beyond the orbit of Neptune, beyond the scattered disk and the Kuiper Belt's icy populations, something may move, slowly, impossibly slowly by human standards, tracing an orbit that takes perhaps 15,000 years to complete, visiting the inner edge of its vast ellipse only once in the entire span of recorded human history. We have not yet confirmed it. The data points toward it. The mathematics favour it. The orbital shadows of smaller bodies lean in its direction like compass needles orienting toward an unseen pole, and we are looking, with the most precise instruments our civilization has ever built, with patient, methodical surveys that cover more sky with more sensitivity than any previous generation of astronomers could have imagined, with a golden mirror hanging in the cold of space, sensitive enough to detect the faint thermal glow of a cold, distant world against the ancient light of the cosmos. The answer may come soon. It may come from a graduate student's careful analysis of a data pipeline. It may come from a slow-moving point of light that catches someone's eye in a deep field survey. It may arrive on an ordinary afternoon in a notification on a scientist's computer, a candidate object, moving at the right rate, in the right direction, at the right distance. Or it may be that the surveys conclude and the candidate does not appear, and the models are revised, and the orbital clustering is reattributed to other causes, and the hypothesis is retired with the respectful honesty that science maintains toward ideas that have been thoroughly tested. Either outcome would be, in its own way, a triumph. Discovery would give us a world we did not know we had. Non-discovery would sharpen our understanding of the outer solar system's true architecture, free from the assumption of a missing member. Science does not lose when it finds absence. It learns the shape of things by the boundaries of what is there and what is not. Tonight, we have travelled to the outermost edge of our solar home, to the cold, dark, ancient reaches where sunlight barely whispers and where the familiar order of the inner solar system gives way to something vast and still largely unknown. We have traced the careful, patient work of astronomers who read the orbital behaviour of distant icy bodies like a language, looking for the grammar of gravitational influence, the syntax of an unseen world. We live in the early years of a century that will, almost certainly, answer the question of Planet 9 definitively. The tools exist. The surveys are underway. The data accumulates. And somewhere out there, at 3 or 5 or 700 times the distance of the Earth from the Sun, in a cold and silent darkness that no human eye has ever illuminated, something either moves in its ancient orbit or does not. The darkness holds its answer patiently. It has been holding it for 4.5 billion years. It can wait a little longer, as can we. Thank you for travelling to the edge of our solar system tonight, for sitting with the uncertainty and the wonder in equal measure, for being willing to hold a question open, unresolved, and find beauty in the openness itself. The outer solar system does not hurry. The darkness at the edge of home is still and deep and full of things we are only beginning to learn to see. Rest now. The search continues without you tonight. Telescopes turning, data accumulating, the patient work of discovery moving forward in observatories around the world, and in an instrument of gold and glass hanging quietly in the space beyond the moon. Whatever is out there has been waiting for billions of years. It will still be there in the morning.